Okay, YouTube, in this video as we prepare to graph polynomial functions, we're going to be exploring what we call the end behavior of a polynomial function. So one nice feature of every single polynomial function is that it presents you with this smooth curve. We say these are curves that basically, they have nice little smooth curves. And the thing here is they will never pick your pencil up. You'll never pick your pencil up from left or right on this graph. And also, there won't be any sharp bends, okay? So all polynomial functions kind of have this behavior. And that being noted, what I want you to understand is this. On the ends here, you'll notice that on the left side of my graph, my y values are falling. And on the right side of my graph, my y values are also falling here. I would say that with polynomial functions, their end behavior is such that their ends, either their y values are going to go down forever and ever, or their y values are going to go up forever and ever. And so what you'll see is that we get these polynomial functions that could rise on the left and rise on the right, but could also rise on the left and fall on the right. Or they could fall on the left and rise on the right, or they could fall on the left and fall on the right. And these would be the four possibilities for what we see as their what we call end behavior. And so when we refer to end behavior, again, we refer to the behavior of the y values, or the f of x values, as the x values do what we say is approach positive infinity and negative infinity. So for instance, on my top graph up here, I would say that as my x values are approaching positive infinity, that is to say, as the numbers that we're plugging in keep getting bigger and bigger this way, what's happening to our y values on our graph? And the way we would write this is exactly like you see here. We'd say as x approaches positive infinity, this means as we go to the right. Our y values here on my graph are going to negative infinity, that is, they are decreasing forever and ever. And on the left side of my graph, which I would write this way, I would say as x approaches negative infinity as we go to the left. Then my f of x values here, we can just see on the graph here, are going down forever and ever. So they approach negative infinity. And so really what we're doing again is just telling whether our graph goes down forever and ever or up forever and ever on the left and right side, or as our x values approach negative and positive infinity respectively. So what we're going to do in this video here is we're going to be looking at the effect of the degree in the leading coefficient upon the end behavior of our graph. We know it's one of these four possibilities. Could we narrow it down just by looking at this leading term if we have our polynomials written in standard form? So what I've done is this. We have f of x, g of x, and h of x here. And what I ask us to do is use a graphing calculator to graph each of the following and then comment on their end behavior. So I've set us up down here, and in each of these possibilities you'll see that I've written here as x goes to negative infinity, as x goes to positive infinity. That is to say, as we go to the left side or the right side of our graph, what are our y values doing? Are they going up or are they going down? So all of these, I want you to notice that x squared is the degree of this one. Here we have a second degree polynomial here. We'll point this out. We have a fourth degree polynomial here, and yes, I did go in order, but we have a sixth degree here, and yes, they're all even. So when we look at their graphs, let's go over to Desmos here. I could use a graphing calculator also. Here's our squared or quadratic polynomial. And so we recognize this parabola. Of course, we always associate parabolas with second degree things or quadratic things. But in terms of end behavior, we would say that on the right side, as x is going to positive infinity, as the numbers we're plugging in are getting bigger and bigger, our right side of our graph is going to positive infinity. And the left side of our graph also rises or goes to positive infinity. So on our papers here, we would say, well, this goes to positive infinity, and so does this. This goes to positive infinity, or it's going up. So now looking at our second graph, flip back over to here, we have this fourth degree thing here, and I notice that on its right side and on its left side, it's also rising on both. So its y values are approaching positive infinity on both of these. And then as we look at this last graph here, we also have this sixth degree thing that gets a little bit more bendy in the middle here, but also rises on the left and right. So these approach positive infinity and negative infinity, or positive infinity on the left and on the right. So now what I want to do for these three down here, we have a first degree thing. Let's point this out. We say this is a first degree thing. This is a third degree thing. This is a fifth degree polynomial. Yes, these are all odd, but what I want to do is determine their end behavior by looking at their graphs. So again, we'll go over to their graphs here. Our first graph is x plus 1. We say x plus 1, well, that's just y equals mx plus b. It's got a y-intercept of 1, a slope of 1. But its end behavior is that on the right side, as our x values go to positive infinity, our y values are going to positive infinity. But on the left side, as x goes to negative infinity, as we go to the left, those x values are giving us more and more negative y values. So our y values are decreasing on the left side. So we would say on the left side of this graph, our y values are going to negative infinity, but on the right side, our y values are going to positive infinity. How about for our cubic function here, third degree thing? So we're going to take a look at it. Here's our third degree thing, and I notice that also on the right side of this graph, our y values are going to positive infinity, while on the left side, we're falling, we're going to negative infinity there. So we say on the left side, we proceed to negative infinity with our y values, but positive infinity with our y values on the right side of the graph. And then our last function here is a fifth degree, or actually what we'd call a quintic function, but also same end behavior. So falls on the left, rises on the right. So what I asked down here is what is true about the left-hand side, or we'll abbreviate this LHS behavior with the RHS behavior of the graph when the degree of the polynomial is even and when it's odd. And what I want everybody to see here is that when we had even degrees, the left and right-hand side behavior are all the same behavior. And if you look at your odd degree, you see that we had opposite behavior here. If one side was falling, the other side was rising. So we're going to make a little note down here. We say even degree. What does the even degree imply for us here? We say left hand side, right hand side behavior is the same. And I just don't have a lot of room down here. That's why I'm kind of writing all this way here. But you could fit it on your paper a little bit more easily. We say odd degree. Odd degree just basically means we're going to get one of these two situations right here where it's opposite behavior. So we would say LHS, RHS behavior. Opposites. Okay, so that's the nice thing about the degree. It'll tell you the end behavior of your graph, either the same or different. Now, when we look at this second portion, I say let's regraph each of these in the previous exercises, but make their leading coefficients negative. So we're going to do this again. In all of these functions right here, what I'm going to do is I'm just going to go back over to Desmos. I'll turn this back on. I'll put a negative in front of here. And you can see that the end behavior of the graph on the left and right, this is a second degree thing, is still the same, but they're both falling instead of rising. Again, if I turn this one on here and I put a negative here, let me get this out of the way. It's both falling on this one. And then on this one here, if I put a negative for a leading coefficient, I have falling on both sides. So we're going to pop in these values here. We would say goes to negative infinity, goes to negative infinity on all of these when we put a negative leading coefficient in front. And then for all of these down here, when we drop a negative leading coefficient in front, I'm just going to turn them all back on. We can see that they were falling on the left, rising on the right. When we put a negative in front here, you can see that their end behavior inverts itself. So they're all now rising on the left and falling on the right. So when we look at this here, we say rising on the left. That means on the left-hand side of all of these graphs here, whoops, there we go. We were rising on the left, but falling to negative infinity with our y values on the right. So here's the interesting thing. We say what's true about the right-hand side behavior of the graph when the leading coefficient is positive. The thing here is this. When we had positive leading coefficients, we'll go back and look at these. The right-hand side behavior of the graph, let me get out the red here. When we had positive leading coefficient, the right-hand side behavior of the graph was positive. And when we had negative leading coefficients, going back over here, the right-hand side behavior of the graph was tending towards negative y values. So what we're going to write here is this. Essentially, when the leading coefficient is positive, then we have the right-hand side behavior. Oh, that's horrible. I'm sorry, you guys. The right-hand side behavior of the graph. Behavior is that f of x goes to positive infinity. So basically, the leading coefficient tells you, whether it's positive or negative, tells you whether or not the right-hand side of your graph is going to rise or fall. So when it's negative, we say the right-hand side, always tells us the right-hand side. I'm going to do this better this time. We say behavior is that f of x goes to negative infinity. So putting this together, we could always determine the end behavior of your graph before you even graph it. So the last thing we're going to do in this video is I included a table here that generalizes everything we just said. If the degree is odd, look at both of these first instances here, we'd say that the left-hand side and the right-hand side behavior of the graph can't be the same, okay? And then we would say that if the leading coefficient is even, the degree is even, then the left and right-hand side are the same. And then the next thing was this, we'd say if the leading coefficient is positive on this side, on the left column here, we can see that the right-hand side of the behavior of the graph is up on the right side. And if the leading coefficient is negative on the right side of your graph, we are falling. So what we're going to do here is we're just going to determine the end behavior of this graph without even graphing it. And I notice that this is already written in standard form. So two things we want to list here are the leading coefficient and the degree. And I guess not necessarily in that order. Usually I guess I'd go for the degree first. So we'd say the degree is third. I am going to write a little note here that this is a cubic function. But I'm also going to write this. It's odd. Also the leading coefficient, which is equal to negative 0.3. I'm going to make a little note here that this is negative. So the things that I can determine about my graph before I even graph it, I'll say, well, say that I have some graph that I don't know what it does in the middle, but on the ends I can tell you what it does. I would say the first thing that I'm going to glom onto is the fact that the leading coefficient is negative. The moment I know that that's negative, I know that the right-hand side of our graph must fall. And also on the oddness of our degree here, I know that the left-hand side behavior of the graph must be different than the right-hand side behavior of the graph because odd degree functions behave differently on the left and right-hand side. So our graph must rise on the left and fall on the right. So we could write this in an abbreviated format as up-down orientation for the graph. So now, that being said, we do actually need to be able to write this in a formal format. So we are going to do that, and we have to do this on every problem. But I want you to know that you can write it like this or illustrate it like this when we graph functions. So in either instance, we're going to write as x approaches. In the first instance, we say as x goes to the left, as x goes to negative infinity, what are our y values doing? And as x goes to positive infinity, what are our y values doing? We can just borrow from our little notation here, and we could say, well, on the left-hand side, our graph was going to positive infinity. And on the right-hand side, our graph must go to negative infinity. And I would encourage you to go graph this function here to check to see that it actually does this. So in the next video, we're going to use end behavior and plugging in points to actually graph a polynomial function. Cheers.